bit of a change in plan, so let's say that the presentation might have some, let's say, some pitfalls. So today I'm going to introduce as Laurence has mentioned before, the MONBON project that is led by the Symbios Laboratory in collaboration with the team by Yves Gerlin and with Matthijs in Lyon. The idea of this project, as Laurence has already mentioned, is deriving from a European project funded by the European Space Agency. And I'm going to tell you a few details about it as well. But the interest, let's say the scientific interest behind this project starts from the idea that we want to develop new ways to understand how bone functions. And so bone, I hope I'm not going to go into too many details on the biologics of bone, but the idea is that, I mean, bone is basically, its function is due to the interaction of many different cell types. And all these cell types derive from different precursor cells. Okay, so, in this case, I mean, like, let's say we have a stem cell that is able, under appropriate stimuli, to develop into an osteoblast, and then into an osteocyte. But then there are other precursor cells that are able to give birth to different cell types, to the other cell types. Bone is a very active organ, where basically and it responds to the mechanical stimulation that we exert on it, but also to damages. So, for example, if we take into account that there are small fissures that are created into the bone, cells respond by releasing molecules. One of them is RANKL, that is let's say the molecule of interest in our study. This molecule is sensed by the environment, and indeed, I mean, it's taken up by other cells that respond by differentiating into cells that are able to resorb bone. They are called osteoclasts. And therefore, we get to bone resorption. Now, when we have an imbalance between bone deposition and bone degradation, let's say, we have one of the typical illnesses that is osteoporosis. And I'm saying this because, so we can use basically RANKL as a biomarker for osteoporosis, but in order to develop countermeasures, there are a number of different models that have been developed. Among the in vivo models, there is one that is used in our laboratory, and in order to understand how cells or how the whole animal responds to this, to the stimuli, for example, in this case is an unloading model that is basically where the mouse is not really using its legs, so it induces basically something like osteoporosis. We can use a number of different techniques, like the ones that you can see described here. One of the most common is the ELISA, that is the closest to the technology that I'm going to be talking about today. On the other side, we have biosensors that have been developed, like based on electrochemical impedance or field effect transistor or organic electrochemical transistors, but today we are going to be focusing on surface plasmon resonance-based devices. I told you that in vivo models are one of the possible models that we can use. On the other side, as we tried to do during the bonus project, that is the project funded by the European Space Agency, we were trying to develop an in vitro model, so a culture chamber where we can put the cells and we can try and see how stem cells, respond to mechanical stimulation as exerted by shear stress, so fluid movements, let's say. And the idea was to basically connect the culture chamber to biosensors. This was originating from previous work that I have done in the past, where we were using an organic electrochemical transistor functionalized to detect specific biomolecules. And the idea was to basically further expand this technology, detecting a variety of biomarkers that can be connected to cell metabolism, cell proliferation in general. So you can imagine that cells during their growth, their differentiation, secrete different molecules, and we can use this to follow their behavior over time. So this is a bit of a background of what I'm actually going to be talking about. That is the MON project, sorry. So it's going to stop? Maybe no. Okay, so the MON project starts from a technology that has been patented at Tubercurian by Yves Jorlan and Nicola Crespo Monteiro. I mean, the advantages, maybe many of you know about them, but the idea is that, I mean, like we can have real-time and fast measurement, high sensitivity, selectivity, and it's label-free. But also the technology is, let's say, supposed to be portable, and of course, one of the main interests is that we can have spatial resolution, which means, for example, that we can functionalize different areas and detect different biomolecules on a single device. What I was referring to is that, I mean, we can functionalize the surface of this device with capture molecules that are gonna specifically detect selected target molecules, as in this case, RANKL. I'm not going to go into the details because obviously I didn't take any PhD in physics or optics, so I remand to Eve for questions about the specifics of the physics behind the technology, but let's say that from the conventional approach that was based on a change in the refractive index, we moved to, I mean, Eve's team moved to what is called the switch approach. And therefore, yeah, that is basically based on a combined approach of laser interference lithography combined with photo nanoimprint, as you can see. And basically we have then a conformal layer of gold that is deposited into the ammonite layer that has been patterned. So the work that Sarabjit Kaur has done in the months that she has been working with us has been mostly focused on developing the microfluidic chamber or improving the microfluidic chamber that is connected to the device. The main objective here was to reduce the dead volume. When we say that volume, we refer to the overall amount that we have to, that is connected to the tubing and to the fluidic system itself. And she developed a very simple but very smart approach that was based on parafilm, as you can see here. So basically she was creating an area within paraffin that I guess every one of us has seen in their life in the laboratory, and basically she was, by a thermal treatment, she was sticking it to the other surfaces. And with this, she managed to reduce the dead volume to 10 microliters. That you can imagine that for biological samples is very interesting and highly important. Because many times when we work with recombinant proteins, with proteins that we have to buy, these are very expensive, so we have to work with very little volumes. Then the next step has been basically to, it's going to be, let's say, to develop a functionalization procedure. that starts with basically functionalizing the surface, the gold surface with the thiol moiety, and then basically attaching proteins. And in this case, we are going to be working with antibodies that are proteins that are able to specifically recognize a target biomolecule, and then with an ethanolamine step that is basically the blocking step. All these different steps of the functionalization are going to be characterized with different technologies. I'm not going to go into the details, but if you have questions, I'm going to be happy to discuss about them. And here I'm going to just be listing some of them. So we're going to be using XPS that basically gives us an idea of the surface chemistry. We are going to be using ATR, FTIR, so that gives us also the chemical footprint of the surface, and fluorescence microscopy as a way to see the homogeneity of the functionalization. And of course, all of these, comes before the actual detection of the target biomolecules online. That is basically part of the future work that is going to be done. That is basically to validate the functionalization strategy. And the aim here is to be able to have sensors that are highly selective, but also specific for RANKL. And then further work is also going to be going into optimizing the sensors platform and trying to integrate the established sensor platform within the culture chamber, where we are actually going to have stem cells differentiating into bone-forming cells and therefore secreting RANKL. But all of these, of course, after having validated the developed platform. And with this, I realized that maybe I was a bit fast, but I'm going to thank you for your attention, and if you have any curiosity or any questions, I'm happy to take them.